with our topic, which is equilibrium of rigid bodies. So this one, it's actually continuation with the force system and the resultants. So here, for equilibrium of a rigid body, what we're going to do here, instead of getting resultant, we are going to now understand what equilibrium is. So equilibrium is the state of body which is in balance. I mean, the body is in balance position. So how do we make the body in balance? So in order for us to conform to the equilibrium concept, all we have to do is get the concept of equilibrant, where the equilibrant is the force equal to the magnitude of the resultant force. Remember the resultant, the force vertical and horizontal. So it's actually Rx or Ry, and that's equal to the summation of forces horizontal and vertical respectively. That we need that resultant for us to be able to equate that as our equilibrant to make it equilibrium. So it's actually the force acting is in opposite direction and is in collinear with the action of the resultant. So if the resultant is vertical, then our equilibrant is vertical, and then if our resultant is horizontal, then our equilibrant is also horizontal. So in that manner, we'd be able to have it visualized. By the way, for example, if we have different forces here, we need the resultant, right, to represent the whole forces. So we need Ry for that vertical, and to satisfy equilibrium, we need is in the opposite direction with the resultant, but in the same magnitude. So that's about the vertical. How about for remembering, by the way, that Ry is equal to the summation force vertical. So since it's now equilibrium, since Ry is just equal to Ey, or equilibrant in the vertical sense, or in vertical y, then somehow it's now equal to 0, since Ry is just equal to Ey. So there is no force that makes it imbalance, but rather the force is equal in magnitude but in opposite direction, so it's now balanced. So for example, if we have horizontal forces, then we have to, and then for that we need the equilibrant for all the horizontal forces that is represented by Rx. So remembering that Rx is just the summation of some forces horizontal or along x, then could be, or it would be now, the summation of forces x equal to 0. That's how to satisfy equilibrium. So therefore, equilibrium equations rotates or involves only 3 equations. Remember, the force vertical y, the force vertical y, you will be getting the sign convention, and that would be positive, upward, and downward negative. And then for the force horizontal or along x equal, then we will have sign convention to the right positive and to the left negative forces. And then for the summation of moment equal to 0, for the last equation, we will have the summation, moment clockwise positive and counterclockwise negative. So we are not getting the resultants anymore, but rather the resultant would now be equated to 0. So the resultant is just equal to the summation of forces. Then therefore, summation of forces now would be equated to 0, and the summation of moment as well. Okay, so by the way, I'd like you to get acquainted with the different supports and support reactions whenever there are supports we used in particular situations. So I want you to get familiar with the different supports that we will be using all throughout the problem, all throughout the equilibrium and the rest of the topics, or the remaining topics that we have. So for example, if we have hinge, so that's a hinge. If we are going to translate it into force, then hinge will provide us two forces. So that would be two forces, vertical and horizontal. Or one is perpendicular with the line of action, or with the beam, or with the structure, its line of action, and the other one is horizontal, or in the same line of action. Next is a roller. So whenever a roller is given, then the equivalent reaction would be perpendicular with the line of action. So the line of action is horizontal, therefore the equivalent translation of the force would be perpendicular, and perpendicular of horizontal is vertical. So let us proceed to the next one, fixed. So again, I want you to get familiar with the different supports, because we will be translating the supports into equivalent reactions. So for fixed supports, so for example, that one in the left side, so there would be three equivalent reactions. So one is perpendicular with the line of action, the other one is on the same orientation with the line of action, and the third one is a moment or a rotational reaction. So that is fixed support. And then those three, by the way, the hinge, roller, and fixed, those are the primary supports that we will be using in the later part of this course. Then for cables or links, so cables, this is actually used in hanging bridges, and then links, we're actually using this one in connecting two bodies. So basically this is a cable or a link, then we are going to translate it the way the cable is laid. So for example, the cable is vertical, then the force is vertical, but it's always pointing away from the body because it's a cable, it's good intention. So good intention meaning it could be stretched out. So that's a cable or a link. So again, orientation of the link, or the translation of the link, is on the same orientation with its support. So if the support is vertical, then the orientation would be vertical, and then it should always be pointing away from the body. And then if the support or if the link is inclined, then of course it should be inclined, or in this line of action with the supports cable, and it should always be pointing away from the body. Next is we have the rough surfaces. So actually this rough surfaces, most of the examples here, or basically the examples here for rough surfaces, you'd get to encounter it in your dynamics of rigid bodies. So it's on the next course after this one. So rough surfaces, meaning we are going to consider now friction. So for example, that is the rough surface support. So there would be vertical and horizontal, or there would be normal as the vertical and horizontal as the resisting friction. So there would be two reactions. And then for the support smooth, then it's going to be only the normal force, or the perpendicular with the line of action, or vertical. So those are the supports. Let us now consider a free body diagram. So what is a free body diagram? So according to the definition, it is a sketch of a structure, or the body itself, that is relieved external supports and replaced with the corresponding reactions. So replacing the corresponding reactions, meaning it's important to really get familiar with the previous things that I had mentioned. So we are going to translate good together with the body itself. So again, we are going to replace it with the corresponding reactions, where equations of equilibrium are formulated for the analysis of the structure. So for the analysis of the structure, it could be beam, frames, and trusses, cables, and a lot more. So without this diagram, one will find hard time formulating the equilibrium equations. Equilibrium equations are the three equations: summation of force, vertical, horizontal, and moment. Remember that. And then it is the most important step in analyzing the structure. So again, a free body diagram is a body itself that we detach the body from the supports. So here is an example. So let's just try to draw a free body diagram. So as you can observe, on the left side there is a fixed support, and on the right side there is a roller. So We have to remember that a fixed support always gives us the three equivalent reactions: the vertical, horizontal, and the rotation. And then the roller would always give us one force only. So that's perpendicular with the line of action. So as you can see, in A, it's a fix, and then at C, it's a roller. So translate A, so it's going to be vertical, horizontal, and moment. And then at C, we removed the support ng roller and we translate it with a different force. So now this is the free body diagram. So the body with the translated reactions. So in this type of illustration, then the next thing to do is get the equations done, like the summation of force, vertical, horizontal, and moment. So those are the three equations that we will be revolving our equations or our solutions to. So let us proceed to our example.